Right, having looked at the condition for hydrostatic equilibrium of a fluid, let us move on now to fluid motion itself. We now have in mind the motion of a fluid in streamlines. You are already familiar with the idea of streamlines, namely it is some kind of smooth steady flow, and I will explain these terms carefully as we go along, but it is flow which is not chaotic or turbulent as opposed to smooth steady flow which is not chaotic or turbulent or like a waterfall or anything like that, but a flow which is kind of regular, has you can put a little piece of dye somewhere and it it moves in some kind of smooth curve. So, we have a flow of that kind in mind. Now, the first concept we have to understand is the idea of a current density. In other words, if these are the flow lines of the fluid, if you put a unit area here, an area element, we could ask what is the mass of fluid crossing this area per unit time. Per unit area per unit time, this mass is called the current density J as a function of R and T. It is the mass of at the point R at time t, it is the mass of fluid crossing unit area per unit time, and of course it has got a direction J, and that is the direction of the local fluid velocity. So, it is not hard to see that this is in fact equal to rho, which could be a function of R and T in general, the density multiplied by the fluid velocity R and T. So, by definition the current density J is the product of rho and V here. Now, we could ask, when this fluid is in motion, assuming that there are no points in the fluid which are either sources of fluid coming out or sinks into which the fluid disappears. So, without any sources or sinks, we could ask then what is going to happen to a little volume element dV at some random point, at some point here. There is some fluid which is going in and there is some fluid which is going out through certain phases of this volume element. So, we could ask for what is known as the net flux of the fluid through this volume element, which would correspond to adding up all that fluid which is going in, taking out all the fluid which is going out and subtracting the former from the latter gives you the outward flux of the fluid from that point here, and let us find out what this quantity is. Now, clearly if I use a volume element of this kind which is parallel, whose sides are parallel to the coordinate axes, then the contribution of a velocity vector pointing in this direction on that face would be the component of this velocity vector normal to this face here. So, that would be in this case, if I choose my coordinate system in this fashion as usual x, y, z, this phase is normal to the y axis. So, the current component J y is what is going to play a role here at that point. Similarly, across the other two faces it is going to be Jx and Jz. Now, what is coming in here is Jy at an earlier point dy over 2 to the left of xyz, and here it is dy over 2 to the right of xyz. So, exactly the same way as we found the force on a fluid element was minus the gradient of the pressure. In this case the same argument, exactly the same argument, but using this vector j will tell you that the net flux, the net amount of fluid that is flowing out through this volume element, net fluid flux through the volume element dV is equal to delta Jx over delta x. That is the portion contribution coming out from the faces normal to the x axis, plus delta Jy over delta y plus delta Jz over delta z multiplied by dx dy dz, which is dV. So, net, I should write this more carefully. So, let us write this as net outward fluid flux it is equal to this quantity here. This is the mass of fluid that is flowing out through the volume element dV through all the faces of it put together, where you have taken whatever goes in with a negative sign, whatever goes out with a positive sign will automatically give you this quantity here by the same argument, exactly the same argument that we used in finding that the gradient of the pressure gave you the net force minus the gradient of the pressure gave you the net force on the fluid on the volume element. In exactly the same way you end up with this combination here dV. Therefore, the flux per unit volume is just this quantity in brackets. This is the flux per unit volume at the point x, y, z. So, at any point in the fluid at the point r, you have to find these derivatives, and remember these derivatives would occur because each component of this is a function of r and t. They would involve derivatives of rho and v in general, but that is the quantity that appears in the flux per unit volume. This quantity has got a name, this thing here. Notice that you could also write this as del dot j. And the reason you can write it in this form is because Jx, because J recall is Ex Jx plus Ey Jy plus Ez Jz, and the del was an operator which looked like this. So, you can write this as a dot product of this vector operator del with the current density J. This quantity is called the divergence of J, and is sometimes written as the divergence of J in words. I emphasize again that this idea of the flux per unit volume at a given point is applicable to any vector field at all, does not have to be the current. Any vector field such as the electric field or the magnetic field and so on, the flux per unit volume for by calculating the flux around an infinitesimal volume element at any point is defined as the divergence of that vector field at the point, and in Cartesian coordinates it is written in this form or in this form here. So, this is not the definition of the divergence, it is an algorithm if you like for finding this quantity here is an algorithm for finding the divergence. So, the divergence itself is defined as the flux per unit volume of a vector field at any point here, and what we found here is the flux of the current density, which in the fluid case happens to be rho times V. But what is this quantity equal to? What is this going to be equal to? And that is interesting to ask, because it is obvious that in the absence of sources and sinks you must have the rate of change d over dt delta over delta t rho of r comma t. This is going to be the rate of change of the mass of unit volume of the fluid at the point r at any given instant of time t. It could increase, it could decrease, etc., and clearly if the system has a flux going in and nothing coming out, the density is going to increase, this is going to be positive. If on the other hand the flux is mostly outwards, there is more fluid going out than going in, then this quantity is going to decrease at that point. In any case, this is what is going to balance minus del dot j of r comma t, because this with a minus sign is the inward flux per unit volume, and this is a rate of change per unit volume, rate of change of the mass per unit volume at the point r at time t. So, this has got to be, if there is no source or sink in here, this has got to be given by whatever the flux of the fluid here, the net inward flux of the fluid, which is minus del dot j. So, together these will imply that delta rho over delta t plus del dot J equal to 0 at all times at all points. In the absence of sources and sinks. This equation, which is essentially conservation of matter or conservation of mass here, is called the equation of continuity. And it is a crucial input, because notice that what the equation of continuity is telling us is that there is a constraint on the way rho and J behave. Remember, J is rho times V. So, delta rho over delta T plus del dot rho times V equal to 0 is connecting rho and V. It means these two quantities, these two fields are not independent of each other. Recall what I said earlier, namely the task of fluid dynamics in some sense of hydrodynamics is to determine what rho and V are, this scalar field and that vector field are, given the pressure and the external force and so on and so forth. So, this is the task of fluid dynamics, but you already have, independent of what forces you apply on the fluid, you already have a constraint equation in the equation of continuity. So, we must keep that in mind here before we go on to finding out what the equation of motion actually is. The next step is the following. Oh, before I do that, let us point out the following simple case. If the fluid is incompressible, which is not a bad assumption in many cases. Even in the case of gases, as long as you are not dealing with very high temperatures, or you are not dealing with very violent fluctuations in the density due to different temperatures, or going near the speed of sound in the medium, so that in the fluid, so that you have shock waves and so on. As long as you are not dealing with such velocities or such conditions, then for velocities much lower than the speed of sound in the fluid, essentially the fluid is incompressible. Even a gas is essentially incompressible when it is in flow here. If that happens, if the fluid is incompressible, then rho of RT equal to rho equal to a constant in space and time, which immediately implies that this constant comes out of the derivative operators. This del involves basically differentiation. It comes out, and this quantity is of course 0, and as a consequence del dot V equal to 0. So, this says that wherever you are in the fluid, this must be 0. Such a flow is said to be solenoidal. V is said to be a solenoidal vector. Okay. For reasons we will not go into, that is the technical term, but this simplifies matters enormously, because it says the equation of continuity does not involve the density at all. It just says del dot V, the divergence of V must be 0 at all points. So, it puts a kind of condition on the velocity V here in the very important case of incompressible flow. Okay. Next, we now turn to the real business, which is to write the equation of motion of a fluid element. So, we need to start by writing Newton's equation for a fluid element, and that is now straightforwardly done, because we already know that the force on this fluid element per unit volume is minus gradient of P plus rho times F external, if such a force exists, rho times F external. This, remember, is the force per unit mass, and this is the density, which is the mass per unit volume. So, this term is the external force per unit mass. per unit volume. So, the force per unit mass multiplied by the mass per unit volume, this is the force per unit volume, that is already the force per unit volume. This must be equal to the mass per unit volume, which is rho times the acceleration dV over dt. So, that is the equation of motion of a fluid element at any point r at any time t. Given this quantity and this quantity, you should be able to determine this quantity, assuming that we know rho already. But remember, rho and v are connected by the equation of continuity. So, if you like, in some sense, this equation gives you the dynamics, it is the analog of Newton's second law, it is Newton's second law, and this gives you the conservation of mass. So, together these equations are supposed to determine rho and v. One can divide by rho and write this immediately as dV over dt equal to minus gradient of P divided by rho plus F external, where remember F external is the force per unit mass on the fluid here. So, this is the basic equation that we have to deal with in fluid motion, where a knowledge of this should be sufficient and this should be sufficient to determine this V, but this is easier said than done. It is a very non-trivial task, as you will see, for complications that arise right away, as you will see in a moment. First of all, this is valid even when rho is not constant, even when the fluid is not incompressible, it is compressible say and changes with the space and time, this equation is still valid. The next step is to ask, what is this time derivative here, this acceleration here. Remember that V is a function of space and time here. So, if you follow a fluid element which happens to occupy the point r at time t, then the rate of change of this V with t, the total time derivative, will have two components. It implies that d over dt V of t must be equal to 1 V of r and t must be equal to one part of the time derivative, time change, arises because there is an explicit dependence on time of the flow of the velocity vector at any given point. So, here is the point, this is the velocity vector at one instant of time, a little later it is here, a little later it is here, and so on. Due to this explicit dependence on time here, there is a change of this V with respect to time, and that is of course equal to delta V of r t over delta t. But that is not the end of the story. Plus, there is a contribution which arises because this changes, the fluid element moves as a function of time, and therefore there is a change of its coordinate as a function of time, and this of course is x, y and z. So, there is a portion which comes due to delta V over delta x times dx over dt plus delta V over delta y dy over dt plus delta V over delta z dz over dt. So, the fact that remember now we are tracking now the unit element, we are tracking now the force per unit volume of a fluid element located at the point r at time t, and the fluid is moving perhaps in an unsteady way. So, the velocity field itself changes explicitly with time, and it changes implicitly because the fluid is moving, because this r has time dependence, and the velocity at that point, the rate of change of this r is precisely what we call V. So, this quantity here can be rewritten in the following way, dV over dt, let us forget about the arguments here, it is delta V over delta t plus, now what is this? Well, as you can see, delta V over delta x, delta V over delta y, delta V over delta z arises by taking the del operator, the gradient operator, and acting on a vector V here. So, let us write this out. Let us write this out explicitly. So, you have V x delta over delta x V plus V y delta over delta y V plus V z delta over delta z V. This is V x, this is V y, and this is V z. So, we have the total derivative of the velocity v is given by the partial derivative of its explicit time dependence plus Vx times this, Vy times this plus Vz times that. But you see these quantities delta over delta x, delta over delta y, delta over delta z arise from the components of the gradient operator, the del, the triangle operator. So, this can be written as delta v over delta t plus V dot del V, where this V dot del stands for the following quantity. It stands for this combination of quantities acting on V, the partial derivatives act on V. So, that is by definition V dot del here on V. So, we have this beautiful formula which says that d over dt of this function of r and t is in fact equal to delta over delta t plus V dot del acting on V of r and t. So, the total derivative is the partial derivative with respect to time, the total time derivative is the partial derivative with respect to time plus V dot del, this extra term here appears in the total derivative acting on whatever the velocity vector is out there. This quantity here is like a derivative due to the fact that the fluid is being dragged along, it is being moved along, and it is called the convective derivative. It arises due to the motion of the fluid. So, notice that V appears in two places. We started by writing an equation of motion for the fluid element. So, there is mass times acceleration here. So, we wrote everything down for unit mass of the fluid and we discovered mass times acceleration gave you dV over dt, but it was a total derivative, but in the case of a fluid it becomes a partial derivative plus the convective derivative. This is crucial, this extra thing here makes the whole thing nonlinear because V appears now in two different places in a product form. So, this immediately means that fluid dynamics is inherently nonlinear. We started with Newton's equation which looked like a very simple equation, but it inherently for the velocity field gave us this little piece of complication here which is responsible ultimately for much of the complication in fluid dynamics, not all of it, but much of it as we will see. So, now where are we? Let us write that down. So, the fluid elements equation now has become delta V over delta T plus V dot del on V acting on V equal to minus delta P over rho plus F external. Now, if it should so turn out that this F external is a conservative force such as gravity, namely it is obtained by from the derivative of a potential, then we already know that for a conservative force, and let us write that here, for a conservative force F external, we have F external equal to minus the gradient of some scalar potential which has now the physical meaning of the potential energy per unit mass, because this F is the force per unit mass. So, this must be of the form gradient of some phi such as gravitational potential rho g h, rho g z would be the gravitational potential, then you would have a force in the z direction which is minus g times E z. So, we have an external force which is derived from a potential, and this is the potential energy per unit mass of fluid, and if you put that in, this becomes equal to, in that case, minus gradient P over rho minus the gradient of phi. So, this is the equation of motion of a fluid element, but you might now say, oh, I put in a conservative force, but the fluid also has some viscosity and I never took that into account, and viscosity is not a conservative force, it is a dissipative force because ultimately it represents some loss or dissipation or friction inside the medium. Yes, indeed, that term too exists, and in general this should really be added. So, you should add a rho times F viscous, which is the viscous drag per unit mass of the fluid, in which case you would get here F viscous, and you would continue to get here F viscous. So, it is getting fairly complicated. You can see that already there is a complication due to this quantity here, which I will call a nonlinearity. It is a quadratic nonlinearity. There are two powers of V here, there is a V here and a V here. You would have expected a linear equation because you would have said, well, mass times acceleration, acceleration is the rate of change of time derivative of the velocity, but it is now appearing in an implicit form as well with a V dot del on V here, the fluid. This complicates matters, as I have already said, but this is the equation, basic equation of motion here. Okay. Solving this equation in any really complicated situation is really tough, but we will see various simple cases of it. But I thought I should bring this out to show you how the very basic application of the basic principles, namely just the equation of motion, will give you, will automatically lead you, using the fact that we are dealing with a continuous medium, automatically lead you to this fairly complicated equation. This is called the Euler equation. Actually, I think that Euler's equation is the one that you get without the viscous term, but the literature differs on what the actual terminology is, but it is the equation of motion of a fluid element, and I would like to leave it like that. Our next task is the following. I am going to drop this F viscous because there are models for it which I might mention at the end, but I am going to drop this thing here and assume that you have just the conservative force here plus this pressure gradient, and then we need to have some knowledge of how the pressure changes as a function of the density, and we will look at various special cases. In particular, if you had an incompressible fluid, then there is no problem, things simplify enormously, no viscosity, this is a constant, and then one can actually try to make headway and see where this gets us. In particular, we would like to integrate this equation once to see if there is some analog of something which looks like the energy in the case of particle motion. We found the first integral of the motion was the energy. Can we do the same thing here is what we will look at next.